All right, so let's talk about the three modes of energy transfer. And the first one is conduction. This is heat transfer by touch, where neighboring atoms bang into the neighboring atoms and they make them move faster and faster and faster. And we can see this Bunsen burner here, and it heats up these, and then these bang into these bang into these bang into these, and it's transferred by touch. The major difference here with convection is that convection is the mass movement of molecules from one place to another. And so, we have the cool water descending, the warm water rising, and, we get that mass movement, and the energy is transferred. And then the last one is radiation, and with radiation, obviously, the electromagnetic rays are heating up objects. Now, one of the things that's critical for us to see here is, with this horseshoe, you could see even here, it's not even glowing, right? And then it starts to glow, and then it's really glowing. Now, we know that this part is giving off electromagnetic radiation, but it's not visible. It's infrared. And if you remember, infrared light is coming from any object that has a temperature. Now, this is visible light, and so it's up at a high enough temperature to shoot out actual visible photons of light. And so, if we take infrared pictures like this one, we can associate different infrared rays with different temperatures, because we know certain temperatures produce certain, wavelengths of light. Now, absorption and emission come, with different surfaces on Earth. The absorption here is, on the pavement, black cars, like this one. And then the white is reflecting, and for the most part, even though it is absorbing some. So we know that a good absorber is also a good emitter of heat, and we look at that in terms of emissivity. So it's a number between 0 and 1. Coal is very close to 1 because it absorbs heat really well. It also emits really well. And then metallic surfaces are close to 0. Now, Wayne's law is very critical because, and you do have this on your equation sheet, it's just rearranged a little bit. This is the peak wavelength given out by a certain object based on its temperature. Now, if we looked at that horseshoe, and we're looking at the particular temperature of, the front of that horseshoe, like here, it's going to have a predominant wavelength. It's giving out other wavelengths of light, but there's going to be a predominant one. So what I want you to do is go ahead and calculate what is the peak wavelength of the Earth, and then what is the peak wavelength of the Sun. And so yeah, go ahead and pause the clip and do that. When you're ready to check, you can hit play. All right, so we should get 500 nanometers for the Sun. And then for Earth, it's about 1 × 10⁻⁷. Now, this is infrared. The Earth is shooting out infrared, but the Sun's predominant wavelength is bluish-green. And so it's giving out, the Earth or the Sun gives out other wavelengths, but its predominant one, the one that it gives the most of, is that particular wavelength. So in this simulation, we can see, if we move this dial up to the Sun's temperature, we end up getting, a peak wavelength of bluish green, but again, it's shooting out infrared as well as ultraviolet. So in this picture, these reflectors are reflecting a lot of light. You can see the chrome reflecting a lot of light there, but there's a lot of light being absorbed here. And this is a critical factor when we're talking about, the big picture of the Earth and, what's absorbed, what's emitted. And this is called albedo, where we look at what's scattered versus what's incident. And snow scatters most of the light coming in. Charcoal is, absorbs most of it. And we know, intensity is power divided by area, so we have that as well. So let's say that we have light from a flashlight hitting a surface with 75 lux of intensity, and it reflects 70 lux. What is the surface's albedo? So yeah, go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay. So area is 0.14, so we can solve for the power. So the incident power is 10.5. The scattered power would be 9.8, so we would get a albedo of 0.93, so it's reflecting most of it. An easier way to do this might be, we know that power divided by area is intensity. So area times intensity is power. So we could take this over this, right? Area times intensity incident divided by scattered, and the areas are gone, so we could just take the intensities and divide them. We get the same thing, 0.93. So we spent some time looking at this today and just remind ourselves what's going on with greenhouse. You know, the sun is emitting the light into the earth. Some of it escapes, some of it's reflected off, some of it hits the surface and reflects off, some you know, is actually absorbed into the atmosphere. Some makes it all the way to the earth. Now once it gets to earth, earth shoots out infrared. Now if you notice here, this is, you know, showing what the earth is shooting out, and the greenhouse gases absorb that. Some of it go into space, but a lot of it comes back to earth. Now when it comes back to earth, the earth absorbs it again, sends it back out, and it's a cycle here where some of it leaves, but you know, a lot of it comes back. That's because the greenhouse gases absorb those photons and it excites those molecules, and then, you know, it shoots it back down to earth. Here's another picture, you know, of the greenhouse gas effect, and you know, just there's multiple different ways to do this. These are called sand key diagrams, where, you know, the actual length of these columns correspond to the widths, or the widths correspond to the actual amounts there. Okay, and then yeah, here's with another picture, you know, just to show that, depict that. All right, so black body radiation. Any object that has a temperature and has a surface area is going to send out a certain amount of thermal energy, and so we have that power is equal to the emissivity times the Boltzmann's constant times the area times the temperature to the fourth power. And yeah, the closer emissivity is to 1, the dark and dull is closer to 1, bright is closer to 0. And yeah, we'll work one out here. So let's say that we have a dog that is out at night. The emissivity of the dog is 0.75. The temperature of the dog is 37. The outside temperature is 2. And so in this one here, we can, and we want to figure out the total energy loss in 35 minutes. And so here's our dog, and we can write this out. Now I'm going to do this with you because it's very easy to make a mistake here. We have the emissivity, we have Stefan Boltzmann's constant, we have the area exposed, and then we have to do something very particular with the temperature. What we have to do is, you know, if it's colder out, you're going to be radiating out more heat, right? And so this dog's temperature is 37. The outside is 2, so we do 37 plus 273 to get it in Kelvin. Then take it to the fourth power. We take this, then take it to the fourth power and subtract them, and we should get 67.284 watts of power coming out. And yeah, and then after 35 minutes, we can figure out, you know, we know power is energy over time, and we can figure out our time is 2100 seconds, and so this is going to be 141,000 joules is what the dog is going to emit outward.